Buon pomeriggio a tutti, sono Giulia, uno dei volontari di BergamoScienza. Le conferenze della 22esima edizione di BergamoScienza sono rese accessibili a persone con disabilità motorie e sensoriali, cercando di garantire luoghi privi di barriere architettoniche e grazie a servizi di traduzione LIS. Tutte le conferenze sono videoregistrate, alcune delle quali trasmesse anche in diretta streaming. Le conferenze con ospiti stranieri prevedono la traduzione simultanea. Le registrazioni verranno pubblicate sui nostri canali ufficiali al termine del festival. Questi servizi sono resi disponibili grazie a Fondazione della Comunità Bergamasca e Fondazione Banca Popolare di Bergamo, che insieme a BergamoScienza sono impegnate a promuovere inclusione e accessibilità. Per la traduzione simultanea è sufficiente scannerizzare il QR code che vi possono fornire volontari in sala o che potete trovare proiettato alle mie spalle. Ok. Il QR code vi indirizzerà direttamente a Converso Web App, dove potrete selezionare la lingua di interpretariato dal menu a tendina. Per l'ascolto della traduzione è necessaria una coppia di auricolari. Vi chiediamo la cortesia di utilizzare le vostre. Chi ne fosse momentaneamente sprovvisto può chiedere ai volontari in sala. Vi do il benvenuto all'evento di questo pomeriggio, intitolato Leggere nella mente grazie all'intelligenza artificiale. Avremo il piacere di ospitare come relatore Jack Gallant, Università della California, e la conferenza sarà introdotta da Chiara Verga, di WeScience e BergamoScienza. Vi preghiamo di silenziare i vostri apparecchi elettronici e di partecipare numerose alle iniziative di BergamoScienza. Grazie per l'attenzione e buon ascolto.
Buongiorno a tutti. Aspettiamo un attimo che il professor Gallant riceva il microfonino per la traduzione.
I don't have my earpiece.
Non ce l'ha. No, ma non... So, this one.
Is this mine?
But this è italiano.
Oh, it had a different piece on it before.
È quello in italiano.
This had a different piece on it before. Okay.
Ok. Buongiorno a tutti, è un grande piacere e onore per me oggi trovarmi qui accanto a una figura di spicco nel panorama delle neuroscienze, il professor Jack Gallant. Come giovane ricercatrice in neuroscienze ho sempre seguito con grande interesse e stima il lavoro del professore, il cui nome è spesso comparso nei paper scientifici che durante la mia carriera ho avuto il piacere di leggere. Essere qui oggi a dialogare direttamente con il professor Gallant rappresenta per me non solo un grande onore, ma anche un'occasione unica di confronto su un tema di frontiera come quello della lettura dell'attività mentale attraverso l'intelligenza artificiale, e spero di potervi trasmettere anche solo un pochino del mio entusiasmo. Il professor Gallant, una delle figure di spicco delle neuroscienze computazionali, è professore di psicologia presso l'Università della California, Berkeley, con le affiliazioni nei dipartimenti di ingegneria elettrica e scienze informatiche, oltre che nei programmi di bioingegneria, biofisica, neuroscienze e vision science. Ha ottenuto il dottorato di ricerca in neuroscienze presso la Yale University e ha successivamente completato il suo lavoro postdottorale al California Institute of Technology e alla Washington University School of Medicine. Il professor Gallant è autore di oltre 200 articoli scientifici pubblicati su riviste ad alto impatto scientifico come Nature, Nature Neuroscience, Neuron e Science. I suoi studi si concentrano principalmente sull'uso della risonanza magnetica per comprendere la rappresentazione visiva e sensoriale nel cervello umano. In particolare, uno dei suoi obiettivi principali è quello di costruire modelli computazionali che permettano di collegare l'attività neurale a esperienze percettive complesse. Questo approccio ha prodotto risultati straordinari, come la possibilità di ricostruire immagini visive guardate da una persona direttamente dai pattern di attivazione cerebrale attraverso l'utilizzo di tecniche avanzate di decodifica. Uno degli studi più noti del professor Gallant, pubblicato su Nature Neuroscience, ha mostrato infatti come sia possibile ricostruire con sorprendente precisione le immagini percepite da un individuo semplicemente analizzando i pattern di attivazione cerebrale, utilizzando sofisticati modelli di decodifica basati sull'analisi bayesiana e su reti neurali artificiali. Questo lavoro ha contribuito in maniera significativa alla comprensione dei meccanismi di elaborazione dell'informazione nel cervello. Quello che rende il lavoro del professor Gallant particolarmente rilevante non è solo il rigore scientifico, ma le sue potenziali applicazioni pratiche. La decodifica dell'attività cerebrale apre prospettive significative per lo sviluppo di nuove tecnologie diagnostiche per disturbi neurologici e psichiatrici. Inoltre, le interfacce cervello-computer che utilizzano questo tipo di tecnologia potrebbero un giorno aiutare pazienti con gravi compromissioni motorie o di comunicazione a interagire con il mondo in un modo completamente nuovo, leggendo l'attività cerebrale e traducendola in comandi o messaggi comprensibili. Oltre all'ambito visivo, i modelli sviluppati dal professor Gallant si stanno espandendo verso altre modalità sensoriali, incluse le rappresentazioni uditive, linguistiche e anche la navigazione spaziale. Studi più recenti hanno esplorato come il cervello codifica e decodifica l'informazione linguistica, utilizzando modelli basati su reti neurali per ricostruire parole e frasi delle risposte neurali. Questa linea di ricerca potrebbe aprire la strada allo sviluppo di interfacce cerebrali che ci permetterebbero alla lunga di poter leggere pensieri e parole, ampliando le applicazioni cliniche, ad esempio, come ho già detto, nella riabilitazione del linguaggio. In sintesi, il lavoro del professor Gallant rappresenta uno degli esempi più avanzati di come le neuroscienze moderne, integrate con le tecnologie di intelligenza artificiale, stiano progressivamente decodificando i complessi meccanismi del cervello umano. Le sue ricerche ci avvicinano sempre più alla possibilità di leggere la mente in tempo reale, con applicazioni che spaziano dalla ricerca di base alla medicina transazionale. Il tema della conferenza di oggi, leggere nella mente grazie all'intelligenza artificiale, non è solo di grande rilevanza scientifica, ma rappresenta uno degli ambiti di ricerca più promettenti e interdisciplinari del nostro tempo. La combinazione delle neuroscienze con l'intelligenza artificiale ci permette di esplorare nuove frontiere nella comprensione dei processi cerebrali, con potenziali ricadute significative sia in ambito clinico che tecnologico. Per cui adesso, senza ulteriori indugi, entriamo nel vivo della conferenza di oggi. Grazie.
Grazie. Thank you for that very kind introduction. I'm very happy to be here in Bergamo to speak to you all about my research. Today I will be talking about neuroscience in the brain. Before I begin, I just want to mention one thing. The newspaper, the local Bergamo newspaper, promoted me and claimed that I won the Nobel Prize. I just want to point out I am not the Nobel Prize winner. The Nobel Prize winner is speaking at 5 o'clock today. That's Frances Arnold from Caltech. She'll give a lovely talk, and I hope you will stay around for it. Today I'm going to be talking about the brain. The human brain, of course, is responsible for everything we experience, everything we know, everything we feel, all of our motivations, desires, future plans, our feelings, our happiness, our sadness, all emanate from this organ, the human brain. The brain is a very complicated organ. It consists of hundreds of individual areas that are distributed across the surface of the cerebral cortex and in many, many structures that are hidden underneath the cortical mantle here that you can't see. There are probably something like 200 to 500 distinct brain areas, and these are all connected together in a very complicated, highly interconnected network. So the physical architecture of the brain is a very complicated, highly interconnected network of where each point in the brain has a 50% chance of being connected to every other point in the brain. So it's a very, very complicated structure. But if we want to understand how the brain actually operates and functions, we can't only pay attention to the anatomy of the brain, we also have to think about what information is being transmitted across these networks and what information is being represented at various different places in the brain. And that is the focus of my laboratory. Now, we have many ways to analyze the physical structure of the brain. We can wait until a person dies and then slice their brain and look at it under a microscope and follow the fiber tracks as they project from one location to another and recreate the networks that way. Or we can use a modern technique called diffusion MRI that allows us to measure the physical structure of the networks in a living person. Measuring the function of the brain is a bit more difficult because the physical structure of the brain is fairly static, but the function of the brain changes dynamically over time as you're thinking. So people have tried to develop methods for measuring the function of the brain for many, many years, and the first person who did this successfully was Professor Angelo Mosso, who was working in the 1880s in Turin, the University of Turin. And Professor Mosso was a physiologist who studied blood flow in many extremities and organs of the body. And he had the insight that if you're thinking a lot, you might have more blood flowing through your head. And if you're not thinking so much, you would have less blood flow to your head. And so he developed a balance where he could measure subtle differences in the weight of the head relative to the rest of the body that would occur if the blood flow was, if there was more or less blood in the head at any given point in time. And then he gave people tasks to either think or not think, and he found that indeed the head became slightly heavier when people were thinking than when they were not thinking. It's a truly fascinating experiment that was recently replicated over the past 10 years. It's been replicated several times using modern technology and more advanced weighing scales. But of course, this only gives you a picture of the blood flow through the entire head. You would like something that's more localized. And in the modern day, we can use something called an MRI machine to measure changes in the functional activity of the brain locally at thousands, tens of thousands of different points in the brain. So an MRI machine is a large stationary magnet, and we put a person on a bed and we slide them into the magnet, and then they perform a task while they're in the MRI machine. This particular task I'm not going to be talking about today. This is a driving simulation. The person has a little magnet-safe steering wheel and pedals and optics, and they drive around in a virtual environment performing a taxi driver task. This just happened to be the picture I had. I won't be talking about this experiment today, but you can do very sophisticated naturalistic virtual reality experiments in the MRI machine. To get a feeling for what the data looks like, it's best to just show you a picture of an MRI scan in real time. So this is a brain. It's folded up very tightly inside the skull, so we computationally inflate it into a beach ball, and we flatten it out. And if we did this to your brain, we would have something about the size of a large pizza. Now, we've got the left hemisphere on the left and the right hemisphere on the right. At the moment, the person is just resting in the MRI machine. To orient you, the visual system is in the middle here. The auditory system is at the lower middle on the left and right. The motor strip is here on the left and the right. And prefrontal cortex is up here on the far left and far right. And this slide shows changes in metabolic activity, changes in blood flow and blood oxygen that are a consequence of neural activity. Neurons are little chemical engines that need to extract oxygen and sugar from the blood in order to make the chemical that they use to run on, and we measure those changes in blood oxygen as people are performing a task. Red locations on this map are locations where blood flow is higher than average at a certain point in time, and blue locations in this map are locations where the blood flow is lower than average at a certain point in time. And what you can see is that as the movie plays, the patterns of brain activity change dramatically across the surface of the brain, depending on what is on the screen. Sometimes there is a lot of, I should mention, there is sound in this movie. I have it shut off now. So sometimes you'll see activity in the visual system. Sometimes you'll see it in the auditory system. Sometimes you'll see it in this location called the temporoparietal junction. It changes dramatically over time. So these dynamic patterns of brain activity are the direct correlates and the determinants of the pattern of thought in the person's head. As they're watching the movie and thinking about different things and having different associations, we get different patterns of brain activity. And the job of my lab is to try to understand how these dynamic, emergent patterns of brain activity relate to various tasks that people could perform. Listening to stories, watching movies, playing games, driving, and so on. So we have very complicated patterns of brain activity and some task that we've given to a participant. And we want to make sense of the brain activity. The first thing you might think of to do this is to just build a brain decoder. And a brain decoder goes from the world, which might be, say, a movie, to brain activity. And so it's going to translate between things that happen in the world into the brain. So, for example, there are two young boys in this frame of a movie, and you might think that there's going to be some place in the brain that represents the fact that there are two young children. And so we can use our decoder to relate the presence of the two young children in the movie to brain activity, and we can create a model that maps anything that could occur in the movie onto the brain activity. Right? And the better we can do that, the better a brain decoder we can build. Now, we don't build this dictionary using words. We build it using computational models, so it's math. But the idea of just a translation dictionary is really the central core idea here. We can go from brain activity to the world, or we can go from the world to brain activity. Back in 2009, we published one of the first paper showing how you could decode pictures that participants saw in the MRI machine purely from activity in the visual cortex. So on the top here, we have 3 images that participants saw while they were being scanned. And on the bottom, we have the 3 decoded pictures. And you can see that these are similar in some ways. For example, the high texture and low texture regions of this Mediterranean image are consistent with the high texture and low texture regions of this image. But it's not the same image, right? Similarly here, we have 2 buildings on the side and 1 farther behind. And here we have the Colosseum, and maybe another building here and a distance here. So these reconstructions are recovering some aspects of what the person saw, but not all of it. And the limitation here has to do with the brain activity. The MRI machine is not measuring everything in the brain. There are 80 billion neurons in the brain, 20 billion in the cortex, and in an MRI experiment, we're measuring about 100,000 points. So there are many, many neurons, millions of neurons contributing to each point that we measure in the MRI machine. Consequently, a lot of the information that's in the brain we cannot actually recover. Now, these metabolic signals are fairly slow. They only change on the time scale of about a second, and the natural world is very fast. But we can still recover some aspects of the world. Here you can see the person saw an elephant or a bird, and you can see that we're reconstructing something that vaguely looks like a shadowy version of what the person saw. But this isn't great. It's not a great level of decoding. Now, these 2 decoded results were back in 2010. Since 2010, the MRI technology has not changed all that much, but what has changed is the availability of AI and machine learning models that we can use to help improve our decoding. And so a lot of groups have dramatically improved decoding lately. This is from Professor Shinji Nishimoto, a former postdoc of mine. He's the one that had done the movie decoding experiment. And more recently, he is decoding fairly well static images that people saw in the MRI machine just from MRI signals in visual cortex. The most interesting example of decoding I think that's come out lately is from Professor Alex Huth at the University of Texas, who was another former postdoc of mine, who has developed an algorithm that can allow you to decode speech directly from MRI signals. This is a very difficult problem because we talk very fast. We can say 5 or 6 words in a second, but the MRI signals are very slow. There's no information in MRI at a time scale finer than 1 second. So bridging between the time scale of speech and MRI is a very hard problem, but with modern computational models, we can do this fairly well. You can see here that these decoded results are getting, in most cases, either the exact match or the gist of what the person was talking about. And of course, it also makes errors on occasion. I should mention that Alex Huth has been working on this decoding problem for 10 years, and until 2023, we all thought it was impossible to decode speech from MRI. And he managed to do it, and no one would have expected that this would ever work. If you asked any neuroscientist, you would not be able to do this. So if you think about brain decoding, there's the potential for brain decoding, and there's what you can actually decode. Potentially, you can decode anything in the brain that is in active working memory circuits. So right now you're listening to me speak, and you probably have your own internal dialogue that is talking to you in your head, and all of that is potentially decodable. What you hear, what you see, your internal speech, that is all potentially decodable. What is not really decodable is anything that is stored in long-term memory that is not in active working memory circuits. So if I ask you to think about the name of your first grade teacher, you can probably do that after a few seconds. And once you remember that name, it can be decoded. But before I told you to remember it, it's locked somewhere in long-term memory circuits in the brain, and neuroscientists have no idea how that information is stored, and they can't measure it, and they can't decode it. But anything in active working circuits is potentially decodable. The limitation on decoding is all in the technology end of things. Most importantly, the quality of the brain activity measurements. For non-invasive measurement, by far the best device we have is an MRI machine. But an MRI machine is very large. It's not portable. There are portable brain decoding methods out there like EEG, electroencephalography, or functional near-infrared spectroscopy. These produce very poor brain signals, and very little information could be decoded using those methods. On the other end, we can move from a non-invasive method to an invasive method. So if we have a patient in the hospital, we can put electrodes in the brain, and those electrodes are measuring the electrical signals of neurons directly, so they can decode very high-quality information, but only from a very, very small part of the brain. The second factor that limits decoding accuracy is the kind of dictionary we're using, the computational model that we have. The third is what type of information are we going to decode? If I decode a movie that you're watching, I know what movie I showed you, and so I have some ground truth about what I should be able to decode. If I put you in the MRI machine while you're sleeping, you're dreaming, I don't know what you're dreaming about. So I might be able to decode something, but I won't be able to tell whether it's the right thing that is being decoded. And finally, of course, computer power, but nowadays nobody worries about that. We can just go rent computers anywhere we want. Okay. So I want to delve more into this idea of decoding, but to focus on decoding is actually not the best way to really understand how information processing happens in the brain. A better way is to think about the brain as an encoding system. So in normal brain function, we have a stimulus that occurs in the world, and that creates brain activity. So this is the encoding direction. When we build a decoder, we're taking brain activity and we're projecting it back into the stimulus. Okay? These are just two directions of the same exact process. In both cases, we have some stimulus, we have some features that are represented in the brain, and then we have some brain activity. BOLD just stands for blood oxygen level dependent signals. So these are the signals we measure in MRI. So in the encoding direction, we go from the stimulus through some feature space represented in the brain to the brain measurements. And in decoding, we go from the brain measurements to the feature space back to the stimulus. So I showed you how decoding works. Let's focus for the rest of the talk on encoding. And in particular, I want to talk about, for the most part, this complicated network that spans pretty much the entire brain called the distributed conceptual network. And this is a system that represents conscious experience, working memory, and ongoing conscious thought. And it has 4 components at a broad scale. The first is it has several modal conceptual networks. These are called modal because they're tied to a specific sensory modality. So for example, there's a vision network that just processes vision. That's located here in the occipital lobe. There's an auditory network that just processes auditory information. That's sort of located here in the superior temporal sulcus. There is a somatosensory network. There's a network for smell. Okay? These modal networks feed into a multimodal conceptual network that aggregates information from all the senses to create a sort of modality-free representation of the world. Now, this is just perceptual information. When you're out in the world and you're perceiving what's happening in the world, you don't merely look at the world. You combine information coming in through perception with information stored in long-term memory. And information from long-term memory also gets mixed into these multimodal conceptual representations. And finally, these representations are modulated and changed and altered depending on executive functions, your goals, your plans, your intentions, your evaluation and appraisal of the world, and so on. And all of these systems are constantly working together to create patterns of thought in your brain. So just want to give you a really simple example here. This is a story listening experiment where people are in the MRI machine and they're listening to stories from the Moth Radio Hour. The Moth Radio Hour is sort of a stand-up storytelling contest where professional storytellers tell usually autobiographical stories about their lives. These are very engaging stories, and people really enjoy listening to them. So now, in this encoding model, we have the stories as the input and the brain activity as the output, and we want to build a model that relates the brain activity to the stories. Of course, a story has many different kinds of information in it, and so we might need to build a different model for each kind of information in the story. So, for example, if we want to build a model of the general concepts in the story, we don't want to use the words. What we want to do is abstract the stories into a set of features that relate to concepts. So there are many computational methods for doing this in natural language processing and AI and machine learning. You don't need to worry about how this is done exactly. I just want to give you the general idea. Imagine that you have a computer that scans through the stories and it realizes that the word eyes, the word skull, and the word hair appear nearby one another in the story. That would indicate to the computer that this part of the story involves a head, the concept of a head, right? And you do this for thousands of concepts in parallel as you troll through these stories. So you take the stories and you convert them into a set of features that represent the concepts in the stories rather than the specific words that were used. Then you simply do regression, where you have your brain data you have your features, and you create essentially a set of weights. Now, in our MRI data sets, in a typical data set, we measure 100,000 points in the brain. These points are three-dimensional pixels called voxels. So this axis would be 100,000 long. And then we might have, say, 2,000 concepts. And each one of these concepts, each one of these voxels would have a vector that represents the weights for those concepts projected onto that voxel. If that made no sense, here's the only thing you need to know. We have a method that tells us, that allows us to determine for each one of these 2 or 3 millimeter voxels in the brain exactly what concepts in the story produced activity in that voxel. That's really the main thing. I presented the methods here in case you're interested, but it's not important to think about the methods. Just remember, we have a method that allows us to recover the conceptual coding, the concepts that each location in the brain favors. Now, if we think about a story that somebody is listening to in the MRI machine, stories have multiple levels of information. They have phonetics and phonology, they have syntax, they have semantics and pragmatics. These are all different linguistic aspects of stories. And we can build a different model for each one of these and discover how these are represented in the brain. And if you look at the low-level features like phonetics, phonemes, you will find that they are represented in auditory cortex. But if you look at the high-level concepts in the stories, you'll find that they're represented over almost the entire brain. And this represents the change from low-level features being represented in these modality-specific networks to high-level, general, multimodal conceptual features being represented in this general, multimodal, distributed conceptual network. So let's think about this conceptual network for a moment. Here we're looking at the multimodal part of the brain. This is the concepts represented apart from the sensory modality that they came in from. This map shows the similarity between pairs of concepts. So in this space, concepts that are nearby one another, like thicker and thin, are concepts that are represented very, very similarly in the brain. And concepts that are represented very far from one another, like thicker and husband, are concepts that are represented very, very differently in the brain. So we can look through this to see that the main axis is material properties of objects versus social concepts. Those are the main distinction the brain makes about concepts in the world. But what we really want to know is how are these represented on the brain, and to do that, we can simply take the same map and project it onto the surface of the brain. So if you recall, the middle of the map here is, this is the flat map with left and right hemisphere. The middle here is the visual system. These are stories, so they evoke little activity in the visual system. The auditory system is down here, over here on the left and the right. Prefrontal cortex is here, far left and far right. There are 2,000 concepts being projected in this color map, but to make your lives easier, I've just created a little legend here that just shows a few concepts. The main thing you might want to point out or think of is that visual things are in green, visual concepts, social concepts are in red. So you can see visual concepts are represented in many, many different regions in the brain. Social concepts in red are also represented in many, many different regions of this multimodal conceptual network. Now that's a lot of information to think about. Neuroscientists, nobody can keep that much information in their brain. It's just too complicated. So let's just simplify it. Let's just think about one concept. People listen to stories in the MRI machine. Every once in a while, the story is about a dog. Maybe how a dog looks, maybe how a dog sounds, maybe that you owned a dog when you were a child, right? The story is about a dog. We can take all of those dog-related concepts that occur and look to see where part of the brain is activated when a dog occurs in the stories. And what you see is that many different regions of the brain become activated when dogs appear in the stories. Not just one place. There's not one dog location. There are dozens of dog locations. And these, we think, reflect the different aspects of dogness that your brain needs to represent in order to think about dogs. So, the dog activation near the visual system represents how a dog looks, and it responds to pictures of dogs or descriptions of how a dog looks. Dog concepts near the auditory system represent how dogs sound. Dog concepts in prefrontal cortex would represent information about, say, your prior experience with dogs. Maybe you like dogs, maybe you don't like dogs, maybe you're thinking about your dog at home right now who's waiting for you to come home and feed him. Right? And when you think about dog consciously, it seems to you like it's one unitary whole, some conscious blob of dogness. But in your brain, it's never one unitary whole. It's constantly this fragmented, percolating constellation of activity that varies over time. Now, on my website, there's an interactive viewer that you can play with if you're curious about these kinds of data. And this allows you to go in and click on individual locations in a brain and see what they're tuned for. So the tuning is down here on the right. You can see here I'm clicking on red regions, and if you recall, red regions represent social information. So if I click here, you can see this is accused, married, remarried. These are social concepts and social conflict. There are regions in the back of the brain, in the temporal lobe, in the prefrontal cortex that all represent social information. Now, if we spin the brain around and click on a dark green patch, you'll see that this patch becomes activated when the stories contain information about numbers or time or units of weights and measures or money. All of those things tend to be represented in the number network. And the number network also consists of several different number-related representations distributed across the brain. So these brain representations are very, very complicated. I strongly encourage you, if you're interested in this data, to play with the brain viewer. I guarantee it will provide at least 5 minutes of neuroscience entertainment. Okay. Now, given that there are multiple areas that represent each concept, you can think that maybe these multiple areas are hooked together in concept-specific networks. And that is true. You can perform a cluster analysis on these data to recover functional networks from this distributed conceptual network. To really fully account for the data, you need 100 different networks. In the interests of time, I've reduced it here to just 12 different networks. These represent social information, relationships, written communication, discourse, joking and arguing, which are actually represented in different regions, physical properties of objects, actions and measurements, and a lot of information about places and travel. I argued earlier that these networks are multimodal, meaning they're indifferent to whether the information comes in through vision or through audition. And an easy way to test that theory is to present stories auditorily by having people listen to them and to have them read the stories. And when you do those two different manipulations, you see that the recovered conceptual networks are almost identical. They're really indistinguishable from one another. So these networks do not really, they don't really care about, excuse me, let me rephrase that. This distributed network is relatively insensitive to the specific modality that the information comes in on. The idea is that this network is combining information from all of the modalities to try to create a better representation of what is happening in the world. Because many of you in the audience I know are bilingual, you might be curious about how concepts are represented in one language versus another. So we did a lot of work on this. This is work done by my former postdoc, Fatma Denise, who is now a professor at the TU Berlin, Technical University of Berlin. And this group took Chinese-English bilinguals. These were graduate students at Berkeley who came from China. So their primary language is Chinese, their secondary language is in English, and we played them the same stories. We had them read stories either in English or Chinese, and created conceptual maps for the two languages. And this is a different cluster solution, but the critical issue here is whether the cluster colors are the same for the English language and for the Chinese language. And I think you will see they're virtually identical. There's very, very little difference between the conceptual representation for English and Chinese. I don't have it on this slide, but there is one notable difference, which has to do with numbers. For those of you who are bilingual, you may have had a common experience, which is when you hear numbers in your secondary language, you convert them into your primary language to do math. And actually, numbers are the one set of concepts here that do not map between English and Chinese, consistent with that subjective experience so many bilingual people have had. Right. I also mentioned that you need to get information into this conceptual network from long-term memory, because your ongoing mental activity is not just a product of the world. You're not a passive vessel. You are imposing prior knowledge about your life and about the structure of the world on perception in order to make a better model of the world. And we know from neurology studies that the route from long-term memory into this distributed conceptual network goes through a structure at the tip of the brain here called the anterior temporal lobes. And we know this because there are certain patients who have a variant of Alzheimer's disease. It's related to Alzheimer's disease, but it's not the same disease, where they get decay or brain damage in the tip of the anterior temporal lobes. And when this happens, they end up with semantic dementia, meaning that they cannot label the world. They can't use their long-term memory to help them understand the world. They become averbal, they can't speak, they become socially very awkward and don't really want to have social interactions with people at all. They become very lonely and alone, and they tend to just focus on one thing. They just can't deal with a complicated world. It's a horrible disease. It's a degenerative disease. And we wanted to understand this route from long-term memory, so we wanted to image the anterior temporal lobes. Those structures turn out to be very difficult to image in MRI because, for various technical reasons that are not important for this talk, but we spent quite a while developing new MRI methods that allowed us to map the anterior temporal lobes for the first time. And you can see that the anterior temporal lobes also contain rich conceptual maps, just like the rest of the cortex. However, the social information is represented, is emphasized much more in the anterior temporal lobes than it is in the rest of the brain. And this explains why people with anterior temporal lobe dementia, one of the main losses they experience is a loss of any ability to process social information or social relationships. And finally, the last point I want to mention about the distributed conceptual network is, in some ways, the most confusing part. These networks, everything I told you up to now, implied that these networks are stationary and stable and don't change over time. In fact, that's not true. These networks change constantly. And that is because this executive control system that is involved in your setting your goals and plans and in evaluating the world and in attending to different aspects of the world also influences these representations, and it can actually shift the representations to a very large extent dynamically over time. And this is a very nice demonstration of this, I think. In this experiment, we had people simply watching movies. And when they're passively watching movies, you can see that there's a conceptual map, both in the visual system, here in the back of the head, and also elsewhere in the brain, that represents different objects and actions that occur in the movie. If you then ask the person in the MRI machine, just attend to humans, don't pay attention to anything else, you can see that the map shifts to representing humans more. Oops, excuse me, over here, there we go. The map shifts to representing humans more. In this case, the color map has changed, so humans are green rather than red. And when they attend to vehicles, you can see the map shifts to representing vehicles more. So these representations are unstable, and they are actually influenced to a very large extent by the task that you are performing. One way to think about this is, imagine you go home tonight and your dog Fluffy is missing. and you start looking around, where is Fluffy? Where's my dog Fluffy? My dog has gone. And your brain tries to become optimized to become a Fluffy detector, right? Your whole job now is find Fluffy. So you start looking around, you have to recall from long-term memory, where does Fluffy hide? Did I let Fluffy out this morning? Where does Fluffy hide? Could she be in the back garage? You know, you start looking around, you activate these plans that all involve searching for Fluffy. You are looking around the world at where to try to detect the dog, right? Your brain tries to become optimized as much as it can for this Fluffy detection, dog detection task. Now, parts of the brain that are very near the sensory periphery, like your primary visual cortex and your primary auditory cortex, they can't really change very much. But parts of the brain, your prefrontal cortex, which is very far from the sensory systems, those parts of the brain can change dramatically depending on the task. All right, so I told you about this dynamic conceptual network that has these various 4 components. And what I want to emphasize here is this network is, what we're looking at here in these MRI experiments is conscious thought, conscious experience of the world, ongoing conscious experience as people are engaged in these various tasks. So this is the closest thing we have to a machine that can detect consciousness and decode consciousness, thought, working memory, and attention. Now, in the last part of the talk, I would like to switch from a basic science talk to a different topic that is very, very important to me personally, which has to do with potential clinical applications of this technology. And the reason I'm concerned about this is that many mental disorders are fundamentally disorders of thought, right? A mental disorder might be caused by an underlying organic change or brain damage, but the reason that we are concerned about most mental disorders like schizophrenia or autism spectrum disorder or depression is because they change the way people think. And they change thought into a maladaptive way that is undesirable both for the person and which has huge social costs for the families and loved ones around them. So you would think, if these mental disorders are disorders of thought, that we should measure thought, say using functional MRI, to diagnose these mental disorders. But in fact, that's not done at all right now. Mental disorders like schizophrenia and autism and depression are only diagnosed behaviorally. Some disorders like Alzheimer's disease, we can use biomarkers that are molecular biomarkers like beta amyloid or tau sensitive PET imaging. But nobody is using functional MRI to examine these disorders. And I find that personally very frustrating because you can see what we can do in basic science is very rich and detailed. And it seems like this is something that could easily be applied in the clinic. So there are several limitations to clinical imaging. One is the imaging procedure has to be fairly short and easy to standardize. And the second is the imaging procedure has to reveal patterns of thought in each individual person, right? A lot of times in science, we'll use a large group of people in an experiment, but we will just look at the group model. We won't look at the individual participants. In the clinic, in clinical medicine, we have to be able to look at each individual person. We have to be able to do precision medicine, which means we have to be able to pull patterns of thought out of each individual person, and we have to be able to identify individual differences. So this just shows some representative participants. This is the story listening task. So this gives you a vague idea of how similar and how different the brain maps are. You can see that these brain maps are vaguely similar, but they're also very, very large individual differences. And we want to pull those individual differences out of the data. So I have a wonderful postdoc, Matteo Visconti de Eligio Castello, and he was an undergraduate at the University of Torino and speaks much better Italian than I do. And he has spearheaded a wonderful project to move all of our basic neuroscience technology into the clinic. And one of the first things Matteo had to do was he had to develop a new method that allowed you to look just at the individual differences between people. So what this method does is it allows us to take a large group of people, and then we remove one person from the group, and we build a group model, and we subtract that model from the individual person, and what we're left with is only the individual differences. So these are the patterns of brain activity that make that person unique. And the map on the right is the quantification of this. It's a bit complicated, so rather than go through this, I'm just going to show you this word cloud on the left. This word cloud represents the concepts which, for this one individual participant, these concepts are overrepresented relative to all the other participants. So you can see that this person, when they are listening to stories and they hear about daughter or mother or married or woman or sister or husband, their brain is much more active and their social representations are larger than other people. And of course, since this is an individual differences study, you can imagine that every person we measure is different. So here's a different person. This person, when they're in the MRI machine, you notice that most of the concepts that differentiate them from others have to do with opinions and theories and truth. So this person seems to be overly concerned with scientific reasoning and hypotheses and evidence. And you notice that their social representation is just the same as everyone else's, the same as the group on average. This is the third person. You can see that oh, sorry, excuse me, my mistake. This person's overrepresenting emotion concepts. Emotion, understand, admit, thought, certainly, truly, opinion, truth, but also some things about truth, sympathy, feelings. The next person is overrepresenting emotional concepts and scientific concepts. So for all three of these people, we can not only just extract the conceptual map from this person, but we can extract the concepts that make this person's thought patterns unique and make them an individual. I happen to know who all these people are because these are all graduate students in my lab, and in fact, there's a close match between the personality of the people and the brain patterns that we extract here. That's on a casual level. I don't have any quantification of that yet. Okay, so what I've told you in this talk is, first of all, brain decoding is fundamentally limited by the quality of our brain measurements. You don't have to worry today about having your brain decoded because all the portable methods we have of brain decoding are very poor and they can't really decode much. If you need to have a medical procedure where electrodes are implanted in your brain, we can do a very good job of brain decoding. But for normal, people, brain decoding does not work very well yet and probably won't anytime soon. The second thing I told you about was that this distributed conceptual network, which we can recover now using modern computational methods of cognitive neuroscience, and this distributed network reflects your conscious experience of the world. And the third thing I told you is that we can use measurements of this distributed conceptual network to do precision medicine to try to recover thought patterns from individual people. And that will be very, very important in the clinic because you should imagine that people with autism spectrum disorder will have certain patterns of thought. People with schizophrenia will have different patterns of thought, and we'll be able to identify both the general clinical conditions and the different subtypes using this biomarker rather than just using behavior. That's the end of my talk, but I did want to mention one last thing. Oftentimes people ask about the relationship between brains and AI. This has become especially common since ChatGPT became available, and we all know that these online AI tools can do a lot of things that previously only people could do. I didn't have time to talk about that in the talk, but I'd be happy to give you my opinions about this in the questions. Thank you very much for your time.
Grazie mille professor Gallant, è stato davvero interessante, penso che ci abbia veramente permesso di comprendere come le neuroscienze computazionali ci stanno veramente aiutando ad arrivare a leggere nella mente delle persone. Una domanda che mi viene abbastanza spontaneo di porle è che già comunque si inizia a parlare di quella che viene, diciamo, un po' volgarmente definita una sorta di privacy mentale. Quindi, secondo lei, esistono delle misure in che modo, diciamo, possiamo salvaguardare l'aspetto etico e in che modo possono essere sviluppate delle misure che ci consentono di far fronte a questo, diciamo, problema che da qui probabilmente ai prossimi 10 anni potrebbe essere appunto un grande problema rilevante.
I think privacy in the modern internet age is a very serious issue, and I think Europe has done a much better job than the United States, certainly, in trying to maintain some sense of privacy. I know there's the GDPR is a good piece of legislation, and it's constantly being upgraded to try to deal with privacy. Privacy of thought is an interesting idea. Right now, the status of thought as an entity, as evidence or as a physical material, something one might own or use, differs across different countries. So, for example, in the United States, your thoughts are considered, they have the same evidentiary status as, say, blood or hair. So if someone invented a thinking hat and they could put it on you, the government could force you to give up your thoughts, just with the same way they could force you to give up your blood or your hair or your DNA. That's probably not a good thing. That's just the current status of law in the United States. Different countries have different rules on this. Nobody has to worry in the next 10 or 20 years about this thought privacy issue impacting their own lives, because the portable methods we have for decoding brain activity are so poor that they're not going to really recover much information. In the long run, 20 years, 30 years, 50 years, this is going to be a very serious issue, because neuroscience is a very important problem. The neurodegenerative diseases and neural disorders are a huge social cost. So this means that the government is going to keep putting money into improving neuroscience and improving basic neuroscience and clinical neuroscience. And one aspect of that is going to be to improve brain measurements. And so as people develop better and better methods of measuring the brain to do neuroscience, they can also use those better measurements to decode the brain, right? So it's impossible to divorce our ability to decode the brain from our ability to do science on the brain. They're two completely related things. So over time, as science improves and gets better and better, decoding will improve and get better and better, and these ethical issues will become more important. There's a large community of neuroscientists and lawyers right now working to try to develop a firm legal foundation for preserving brain privacy. There are several international organizations that I belong to, and also organizations in the US. Their EU has had several meetings about brain privacy. This has come up in the court system in the US as well. And Chile had a proposal for, the country of Chile had a proposal for a constitutional amendment that would guarantee brain privacy. So this is an important issue that scientists are trying to get out in front of the danger and create a legal framework for ensuring brain privacy before the devices become available that will allow us to decode the brain.
Grazie. Lasciamo spazio al pubblico. Dante, ovviamente. C'è qua davanti.
Buongiorno, grazie per questa interessantissima conferenza. Io non sono assolutamente un intenditore della materia, più lontano, grazie Gianvito. La mia domanda era questa: sviluppando nei prossimi anni, decenni, questa, diciamo, branca della scienza, potremmo pensare che di arrivare un giorno, magari anche non troppo lontano, a per esempio indirizzare un bambino verso un tipo di studio piuttosto che un altro, non so, verso gli studi scientifici piuttosto che gli studi classici, oppure anche scegliere una professione piuttosto che un'altra, ad esempio uno è adatto a un lavoro da tavolino, l'altro invece a organizzare per esempio una comunità in un'azienda, oppure anche, che so io, avere delle informazioni attendibili, per esempio se una persona può essere adatta per sposarne un'altra oppure no, cioè anche di questo tipo sarebbero attendibili di non sviluppando questi studi. Grazie.
That's a wonderful question. Let me answer it at the most general level first, which is, could you use this kind of brain data for learning, to improve learning? And I think the answer is probably yes. And it's for the following reason. Behavior is a low-dimensional projection of the brain. In other words, for any given behavior, there could be a lot of different brain states that led to that behavior, right? You might go out for a beer after this talk, and you might go out for a beer because you like beer. You might go out for a beer because your friends want you to go out for a beer, or maybe you are being paid from the trattoria to drink beer there so that other people will go drink beer, right? There are many different brain states that will lead to the same behavior. And this is a fundamental problem with behavior, is that all you have is behavior, you don't really know what caused it in terms of thought. So if we could measure thought, then we could compartmentalize the different causes of behavior. So if you were trying to have a child, say, learn to read, you can behaviorally diagnose a reading disorder, but it would be more useful to know what aspect of the brain processes underlying reading are leading to that disorder, right? And this would help that. If you, say, wanted to learn to play a musical instrument, for those of you who have tried to learn a musical instrument, it's very difficult at the beginning, especially if you're old. And there are a lot of different stages of musical processing, right? There's cognitive stages and more physical stages. And if you had these brain measurements, you could more accurately determine which stage of processing is being affected and then target that in a therapy or a treatment. So I think in general, yes. In the long run, I think that is the direction that this will move, is we will have a much more sophisticated ability to understand brain processes and to measure them, and that will provide, just like it could provide a precision medicine, it'll provide precision teaching. Yeah. But that will be 50 years from now, right? So, not soon.
Vediamo se ci sono altre domande. Esatto.
Salve. Ho notato sulle slide, la differenza tra l'immagine ricostruita e invece quella che era stata rilevata. Questa differenza è attribuibile solo al macchinario della risonanza magnetica, che è poco accurato, oppure al fatto che alcune di queste informazioni sono già trasformate nel nostro cervello dai modelli di cui parlava prima? E la seconda domanda è: cosa ne pensa delle intelligenze artificiali? Grazie.
Oh, okay, 2 questions. The first question is, both the factors you mentioned are correct. A common example I give is, imagine you go outside the venue and you see a car accident, and 5 other people see that car accident. and then they report to the police what happened in the car accident. The police will get 5 different stories because each person, although they saw the same accident, they interpret it differently depending on their prior information from long-term memory, depending on what they were attending to, their motivation, and so on. So you're right. If we try to reconstruct an image that someone saw, that's an impossible task because anything that's represented in the brain, except at the lowest, simplest level, if we decoded the retina, it would be what they saw. But anywhere else in the brain is going to be influenced by their prior experience. Yeah. One of the problems with doing these naturalistic tasks is you don't always know what the person is doing. For example, imagine you had someone playing poker in the MRI machine. Well, there are a lot of different decisions you have to make in poker and a few behaviors that you have to employ. And at any given point in time, it might be very difficult for you to tell exactly what somebody's thinking, what the sort of latent state of their brain is. And that's always a problem in this kind of research. To answer the second question, since I set you up to ask it, thank you. A question we often get in neuroscience is is to compare ChatGPT and these large language models to the brain. And the question has come up of, are the large language models intelligent? And are they as intelligent as people? And I think the way to think about this is the large language models are an alternate evolutionary path that is, frankly, completely separate from people. Nothing in the structure of these models operates the way people do. And a useful analogy would be the octopus. So you probably have all, since this is a science-oriented crowd, you're probably all aware that octopi are very smart animals. They live in the ocean. They only live 2 years, but they can walk around, they can use tools, they can interact with other animals in very complicated ways. But they have 8 brains, all distributed in their arms, and another central brain. And whatever the octopus does to be intelligent is it's an alien life form, right? And these large language models are also an alien life form. Humans have evolved to do a lot with very small amount of information. So I could put you on a plane and drop you in a foreign country you have never been in. I could drop you in Japan, say, and you would still be able to get around and figure out the basics of what you need to do. You wouldn't know the language, but you would have a lot of other prior information you could use to get around the world and function. So humans can do one-trial learning. You can just show a person an example of a new object, and they will be able to identify instances of that object. They're very fast learners with very small amounts of information. The large language models are completely the opposite. Large language models appear to be smart because they have soaked up every bit of information on the internet for the entire planet Earth, and they've incorporated it into their internal models. And so when you ask a large language model a question, there's probably something on the internet that is similar to that question. And the large language model essentially goes over to that part of its knowledge base and confabulates a new answer that is crafted out of those parts. But it has no ability to just solve problems on a general basis. It's all an illusion. Essentially, all of human knowledge has been put onto the internet, and it contains regularities that reflect the statistical structure of language at all different levels. And the large language models learn the statistical structure of language, and because there's a strong relationship between human language and the world, they implicitly know about the relationship between the questions you ask and the world, but they don't actually know anything about the world. So it's a really interesting field, I think, of artificial intelligence today, but a lot of the work in the field is to try to overcome the limitations of the models and make them more human-like. For example, there's a lot of efforts to give these models a working memory. These models have no working memory. They don't have anything like our conceptual network. The models just try to predict the next word. That's all they do. So there have been a lot of efforts to try to make these models more human-like. Most of those efforts have failed so far, and we don't know when or if they will succeed. But I think the current generation of large language models will quickly be superseded with a new generation that's more powerful. And this is because when you're building software, you can iterate very, very quickly. So the evolutionary path for this new artificial organism that we're making, it will evolve very, very, very quickly. And it's hard to tell how far it will go or how fast. But it will not be like us.
Ci sono altre domande dal pubblico?
Question
Il
back there.
signore là in fondo, sulla sinistra.
Buonasera, è stato molto interessante tutto quello che ha detto, ma io vorrei portarla su un altro tema a cui lei è sfuggito nell'intervista di ieri sull'Eco di Bergamo, quando le hanno chiesto che cosa pensava del sistema mente-anima. Lei ha detto se ne interessa la religione. Allora io penso che i religiosi, con tutto il rispetto, possono formulare delle ipotesi, ma non hanno nessuno strumento scientifico per poter poi avvalorare quello che pensano. E quindi mi rivolgo a un neuroscienziato. Mi sembra che un neurone possa solo o caricarsi o scaricare. Quindi è tutto un gioco di cariche elettriche. Quindi l'ipotesi dell'anima, ce ne possono essere solo due, o esiste o non esiste. È d'accordo che se esistesse saremmo di fronte a un miracolo continuo, nel senso di qualcosa di extra naturale e soprannaturale, se vogliamo, che riesce a calarsi nella realtà fisica, che riesce a modificarla e quindi che riesce ad avere potere causale nelle azioni mosse dal cervello. Oppure siamo semplicemente cervello al 100%. Mi può dire qualcosa di personale al limite, se non vuol dirmi dal punto di vista scientifico? Grazie.
Sure. I was raised Catholic, so I'm familiar with the religious point of view and the idea of a soul. And the thing to keep in mind is a working scientist is not allowed to basically think about the soul as part of the job. And the reason is we can only talk about things that we can measure. The fundamental tenet of science is everything the goal is to measure some stuff, build a model of that stuff, and then predict new stuff. And if we can't measure the stuff, then all bets are off. So topics like the soul are just outside the realm of science. Science really has nothing to say about whether there's a soul or not, unless the soul is manifest in physics, in the physical world, right? And of course, if the soul was just the brain, then that wouldn't be very interesting. You wouldn't need the concept of a soul in that sense. So from a scientific point of view, it's not that it's not a question, it's just a question that is outside the domain of science. It's not a question that scientists can answer. From my personal point of view, I am the ultimate agnostic. I figure at some point I will die, and then I will find out what happens. Maybe something interesting, maybe nothing. I have no idea. So this is, I think, I don't think there's anything wrong with thinking about a soul or a life force or something that, is parallel to our existence and maybe interacts with our existence. It's just not the domain of science.
Grazie.
Any questions? Nope.
Ci sono un'ultima domanda qua davanti.
Salve, volevo chiedere se esistono dei modelli anche per le emozioni, che mi è sembrato di non aver visto. Ci sono modelli, ho visto per oggetti, e se esistono per le emozioni o come le emozioni influenzano questi modelli. Grazie.
Thank you so much for asking that question, because, you know, I have published a paper just recently on emotions, and I should have that slide in this talk. So I am sorry I neglected to put that in. There has been work on emotions, on emotion representation from my lab and from other labs that also have started using this technology. And emotion representation is very rich. There are certain brain structures that seem to represent emotion more strongly than other kinds of concepts, but you see emotional concepts represented and emotional valence represented kind of throughout the whole brain. And I think the reason for that is emotion often determines, you can think of emotion as acting similarly to one of the executive processes, like goals or motivation or attention, right? Emotion is a aspect of your being that will help direct the way you think about the world and the things you choose to pay attention to and the things you choose, the way you choose to process the information. So emotion modulates all of these brain networks. Yeah.
Bene. Penso che con questa domanda abbiamo concluso l'incontro di oggi.
Thank you for having me.
Ringraziamo nuovamente il professor Gallant.
Shut this off.